Math 252, section 7.1, video 5. We're going to start with theorem. This is theorem 7.13 in the book. It tells us what happens, a little bit about the behavior of the Laplace transform of a function as s goes to infinity. So if f is piecewise continuous on the closed interval from 0 to infinity and of exponential order, then the limit as s goes to infinity of its Laplace transform is 0. Proof. Come on. Oh, that's not what I wanted to happen. Let's try this again. There we go. Proof. By definition, since f is of exponential order, there exists constant c which could be any real number. We'll call M1 because we're going to have to deal with two different values. M1 greater than 0. Now let's call this constant gamma instead of c. That's what the book does for a reason. M1 greater, you know what? Instead of following the book, let's call it C1. M1 greater than 0 and T greater than 0. So that f of t in absolute value less than or equal to M1 e to the C1t for t greater than capital T. Also, since f is piecewise continuous on the interval from 0 to t, it's necessarily bounded. F, by definition, of t in absolute value must be less than or equal to M2 for some M2. And for, we already said we're on that interval. So we can write that as f of t less than or equal to M2 times e to the 0t if you want, because your e to the 0t is 1. Now, just let m be the maximum, the bigger of the two, M1 and M2. And let C be the maximum of C1 and C2. Then f of t has to be less than or equal to m e to the ct on the whole interval. From 0 to infinity. Because this value of m is either m1 or m2, so it'll work on one piece of the either from 0 on one of these two intervals, from 0 to t or from t to infinity, and it's even bigger than whatever it is on the other one. Similarly for c. So f of s by definition, the absolute value, is going to be less than or equal to, so it's equal to this integral, and we put the absolute value, we pull the absolute value inside the integral, and it maybe made it bigger. E to the minus st times whatever we have as our upper bound for f, which in this case is m e to the ct dt, which is just going to be m integral e to the t times c minus s dt, which converges. And so therefore, oh, not only does it converge, it actually is equal to m over s minus c. That's what we need to say. And the limit as s goes to infinity of this is 0, just like we said. So this is smaller in absolute value than something that goes to 0, so it must also go to 0. So as long as our function is piecewise continuous and of exponential order, so it's bounded by some exponential function, then the limit as s goes to infinity of its transform is 0. That does not mean that this must be true of every Laplace transform, because there are functions that are not piecewise for which those conditions don't hold. There will be functions for which those conditions don't hold where the Laplace transform will still exist, and those functions, the limit might not be 0. All right, we got time to maybe do an example or two, so let's do an example or two. Let's look at number 5. Let's do number 7. This is number 7 from the problem section in the book. Number 7, find the Laplace transform. And the function we're given, they graph it. They give the function we're dealing with as a graph. This one's going to be piecewise continuous. It's from 0 to 1. Is that 1? That is 1. The function is constantly 0. on the closed interval from 0 to 1, and then it's going to jump, and from 1 on, we have this linear function. And it also goes through the 0.22. So we see that we can write what the function is, f of t. This is the t-axis. F of t is equal to 0 if t is less than 1, and it's just t if t is greater than or equal to 1. So we'll write the definition for the Laplace transform. L of f, by definition, is the integral from 0 to infinity e to the minus st times f of t dt. And we're going to break this integral up and over two intervals because the function's piecewise defined. So we're going to take it over the first interval. It's just going to be the integral from 0 to 1. In this case, it's e to the minus st times 0 dt. Of course, that whole thing is 0. So this is all 0. And we're also going to add the integral from 1 to infinity of e to the minus st times t dt. And now we're going to have to do integration by parts on this integral. And u equals t du equals dt dv equals e to the minus st v dt. V is equal to e to the minus st over minus s. And so this whole thing, L of f, is equal to the integral, uv, so it's going to be minus t e minus t e to the minus st over s. That's going from 1 to infinity, minus the integral of v du. V is negative, so the minus sign from v, along with the minus sign from the integration by parts formula, is going to turn that into a positive. So plus the integral of e to the minus st over s dt. And that integral is from 1 to infinity again. All right. Now, as t goes to infinity, this first term is going to go to 0, and then we're going to subtract. We're going to evaluate it at 1, and we're going to subtract. When we evaluate this at 1, we get e to the minus s over s, and then we're subtracting because it's the lower limit, and so when we subtract that minus sign, it becomes a plus. So plus, and now this integral we can compute. It's just e to the minus st over s squared from 1 to infinity. And again, as t goes to infinity, the second term goes to 0. So we got e to the minus s over s. And then we're going to plug in 1 and subtract. So it's going to be minus e to the minus s over s squared. And for all this to make sense, we need e to the st. We need a negative st to be negative, so s itself has to be negative. I'm sorry, s has to be positive. Well, this is e to the minus s again. This was s squared, and we need s to be greater than 0. All right, that's it. That's Laplace transforms.